Now let's continue the story by talking about how to add 2 points on an elliptic curve. I haven't given you the most general definition of an elliptic curve, by the way, but it's very similar to what we were looking at with this equation, x cubed minus n squared x. If you just have x cubed minus ax minus b, just with just a different coefficient and then another number, that's the most general elliptic curve. So this is pretty close. It has some special properties, but it gives you the feeling. And I'm going to stick with this particular elliptic curve because it's relevant to the congruent number problem. So it turns out there's a way to add 2 points on the elliptic curve. And I'm not going to justify this except just to show you the geometry and just to talk about why we think of this as a way of adding. It's going to be a nice application of the Bezout idea. Remember that since this curve has degree 3, a line should intersect it in 3 points. So instead of using that kind of intersection to construct the curve or to change variables, we're actually going to use that to add 2 points on the curve. Here's how you do it. Turns out the right way to do it is if you have P and Q, and P doesn't have to be this special point. It could be any point. And I'll show you an animation in a second. If you have this P and Q and you want to add them, what you do is you take the line determined by those 2 points. 2 points determine a line. That's going to intersect the elliptic curve in a third point because the elliptic curve has degree 3. And then it turns out you need to, that's not the sum, it turns out you just need to flip it across the axis. The one kind of symmetry that this curve seems to have is that it is symmetrical across the x-axis. And so you flip it over. Turns out that's the right definition of P plus Q. Now, any kind of addition, if it's going to be any kind of decent addition, it should have a 0. Well, it turns out that's the point at infinity. Remember that this picture is only suggestive because there's a few things we have to do. Really, we have to think about complex numbers, and I'll talk about what the picture is. It's a very surprising picture when you actually use complex numbers. And you also have to think about if there's any points at infinity. Well, it turns out this curve goes up and it kind of bends. It's bending to the right here, and then it's hard to tell on this picture, but then it actually starts bending gently to the left as it goes up. And it goes up, 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 and there is a point at infinity in exactly the vertical direction, either very far up or very far down. So there's one point that's way, way up or way, way down, and we use that. Turns out that's the 0 of this addition. So there's a lot one can say about why this is the right definition. One thing that you'd want to check is, for example, I want P plus Q to be equal to Q plus P. Well, that's pretty obvious from this definition because the line is the same whether you say it's determined by P and Q or Q and P. A trickier thing is we would like, let me just insert this real quick, we would like to say, I should have had this before, we would like to say that if I take P plus Q and then plus R, that had better be the same as P plus Q plus R. That would be very nice. It's called the associative law, and it's certainly true for ordinary algebra. It's true for adding angles, like on the circle. It is true here, but it's definitely a lot harder to prove. And basically the reason mathematicians would call this a notion of addition is not this picture. This picture is how you define it, but it definitely doesn't look like adding anything. It's a weird, bizarre picture. But mathematicians have gotten used to over the last couple hundred years to defining something new, and if it satisfies some formal properties like this and a few others for addition, then we say it deserves to be called an analog of addition. And then we explore what new properties it has besides ordinary addition. Okay, let me give you some examples, not to justify it anymore, but just to get a feel for this. What if you double a point on an elliptic curve? That seems to be something where the definition I just gave you wouldn't work. You don't have, if you want P plus P, you don't have P and Q, two different points determining a line. What you do is you let P and Q get infinitely close to each other, and in other words, you take the tangent line. So P plus P, you sort of take P twice, which means take a tangent line at P, let that intersect the curve, flip it over, and we call that twice P. So that's cool. So let me show you the animation here. So here's on Jammer Sketchpad, I've created this elliptic curve, and now here as I change P and let Q be the same, I'm adding this point to this point. Those are my P and Q. I should have labeled them, but it's not such a big deal. And I'm adding those, and remember the addition point turns out to be this guy, the flipped version of the third intersection. And what I can do is, if I want to double a point, I can just make them get really, really, really close to each other. And that's going to give a well-defined point, and it's exactly where you have a tangent line. Now, remember, you're going to need complex numbers for various parts of this, because, for example, if the line gets, let's see if I can do this. No, it doesn't want to do that. Oh, yeah. If the line gets really steep, it doesn't look like it's maybe going to intersect that elliptic curve at all. Well, maybe you're going to need complex numbers to do that. Okay. And so that's something that we always have to bear in mind, that if the picture starts to seem weird in some cases, it might be because complex numbers are secretly necessary. The other thing we have to remember is that point at infinity. And that's going to be helpful if I take, for example, this point. What if I double that point? Oh, it's kind of giving me a fake line. That guy is going to go up. It's going to go up super, super, super far. Well, this guy goes up super far. They actually are going to meet at the vertical point at infinity. So let me go back to the PowerPoint. Turns out, so I'm asking the question, can the double of a point be 0? This is the simplest case of it, looking for a point of finite order. In the circle case, that was totally true. 180 degree, the 180 degree rotation, if you double it, you get 0. Well, what about here? If you have a vertical tangent, like right here, the vertical tangent, like I was just showing on the animation, that vertical tangent is going to intersect at the point at infinity. So right here, and right here, all the 3 points along the x-axis in this picture, if you double them, you go up to the point at infinity, and then you flip it across the axis, but that's still the point at infinity. So it turns out there are at least 3 points, 1, 2, 3, that double to be 0. Well, the point at infinity is already 0, and if you double that, it's still 0. That's certainly a law that's still true for even these weird kinds of quantities. Okay, this weird kind of algebra. So that's very interesting. We've found some points of finite order analogous to the 180 degree rotations or the 60 degree rotations, but they're actually really much more precisely analogous to the 180 degree rotation. Turns out on this elliptic curve, where you have y squared equals x cubed minus n squared x and nothing else, no other constant term, then these are actually the only points of finite order. There's no points that where you triple them you get 0, or you quintuple them you get 0. Turns out other elliptic curves can have more. It's a very interesting thing to study. But for this particular kind of curve, this particular specific elliptic curve, 1, 2, 3, and the point at infinity are the only points of finite order. Now, I was saying before, the reason we're interested in finding interesting points, and in particular rational points on this curve, rational numbers x and y that satisfy the elliptic curve equation. I was claiming that if we found one of those, we would show that n is a congruent number, because we could massage those back into the big X, big Y, big Z. Let me go back to that real quick. We have this relationship between little x, little y, and big X, big Y, big Z. If we find rational x and y, it turns out we can find rational x, y, and z that solve the congruent number problem. Except there's a few exceptions. And in particular, if little y equals 0, it just totally doesn't work. And so, in fact, we might have thought, oops, let's see, it's down to here. We might have thought that, hey, these 3 points, they are interesting points on this elliptic curve. Maybe they always correspond to rational triangles, and we always have a positive solution to the congruent number problem. Every number is congruent. Well, no, because these guys have little y equals 0. These are the only 4 rational points that don't correspond to triangles. So that's interesting. The 4 points with finite order are exactly the 4 points that don't correspond to triangles. So it turns out we've morphed our original problem into another one, and it's a much weirder problem from what we started with, but it turns out to be the key to making some progress. It says finding triangles showing that some particular number n that we start with is congruent. It amounts to finding rational points on this curve, and it really amounts to finding rational points of infinite order on this curve. Things that when you double or triple or quintuple them, you don't get back to where you started. You don't get back to 0. And it's not remotely obvious that that's going to be an easier problem than what we started with. The original one just had to do with triangles. Now we're talking about weird concepts like infinite order and this weird curve that we don't understand and this weird way of adding things. Turns out that there's so much other stuff that's known about these concepts with elliptic curves that you can actually make progress. Okay, so I want to say a little bit more about the addition law, because it's just such a cool thing. As you could probably have told here, I'm not mainly interested in telling you about Burch and Swinnerton-Dyer, because I haven't even told you what that is at all yet. I'm mainly interested in exploring some cool ideas that surround that, because the conjecture itself is just way too complicated for a talk like this. Well, I'll tell you what it is in a certain way soon. But here's another cool thing that comes out of considering this idea of an addition law. Remember what I said was that when you have a circle, you have an addition law that you can add angles. You can just walk around the circle, and it's a nice way to talk about points on the circle as opposed to talking about their xy coordinates. Then I said, okay, we've got this elliptic curve, and we've got a more complicated definition of an addition law, but I claim it has all the formal properties to be an addition law. But I also showed you a picture a while ago that says that if you have some complicated weirdo-looking curve, you shouldn't get an addition law. There should be some natural symmetry. The fact that you can describe all the points on the circle in this nice uniform way and sort of walk around the circle 1 degree at a time is supposed to mean that every point on the circle looks like every other point. This picture of the elliptic curve does not look symmetrical in that way. But remember that really it's supposed to be using complex numbers. So instead of a one-dimensional curve in 2 dimensions, one real number and one real number, it actually turns out to be a 2D surface in 4-dimensional space. Because 2 complex numbers, each of those complex numbers, x and y, will have a real and imaginary part. And so that's 4 dimensions. And so really, the better picture somehow should be a 2-dimensional surface. And this is projective. One of the things about the circle is that it doesn't go off to infinity. This guy does go off to infinity. But remember, when we work in projective space, going off to infinity is not a big deal. You go off, and it's not like you go forever and ever and ever. You can actually sort of get to the point at infinity. And that's the same as the point at infinity way down here. And then you can sort of teleport back. And so this guy actually does close up. If you go from here and you go up, 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 you just go really, really fast, get to the point at infinity, and you teleport back here and you're back where you started. So maybe all of that tells us that there's some other way to look at this curve and really think of it as a surface that closes up on itself, does not go to infinity. Well, what's the simplest possibility of a 2-dimensional surface that closes up nicely and doesn't run off to infinity? Probably a good guess for that is a sphere, but in fact, the thing that's more analogous to a circle when we think about addition laws is a torus, a donut shape. A torus is wonderfully analogous to a circle because if you look at this wireframe, you can see that there's one direction around the torus where you link your fingers through the hole of the donut that's circular. And then if you look at some point on the torus, you can go in that circular direction, but if you go perpendicular to that, you go around another circle. So in a way, a torus is really something that's built out of 2 circles. You just take a circle, and then you make a circle's worth of circles. Imagine taking the circle and sweeping it around to build the whole wireframe. And so in a very precise way, a torus is really a natural combination of 2 circles. And what we can do is we can think of an angle measure on this direction of rotation. That's going to be one way to describe where I am on the torus. And then I also have to say, oh, have I rotated in this direction as well? So it's going to turn out that a torus, a point on the torus, can be described by 2 angles on 2 separate circles in 2 different directions. That is very, very closely analogous to angles on a circle, and it's analogous enough so that, in fact, the addition law works as well in a very beautiful way. So I don't want to go too much more into that because I'm going to go back to the other curve picture, but I did want to mention it's this wonderful thing that's secretly this picture of an elliptic curve, which is called the real picture, and this picture, which is kind of more of a topological picture, kind of gives the shape better, are really equivalent. And it's not obvious that they're equivalent, but it turns out that they are. So let's go back to this question of points of infinite order on an elliptic curve. It turns out that that rather weird kind of question, but that has access to very powerful techniques, is equivalent to our original congruent number problem. So the question is, when does an elliptic curve have rational points of infinite order? And in particular, this elliptic curve for a given n. Does it have any nice points, a point on this curve, whose coordinates are rational numbers, and that when I add it to itself using this fancy technique of adding over and over and over again, I never get back to 0. We can actually ask a more precise question. It's not absolutely necessary for the congruent number problem, but it's necessary to talk about the full version of Burch and Swinnerton-Dyer. You can ask, how many does it have? Well, I have to say a little bit about that. If you have one point of infinite order, like p on this curve, then 2p can't be the same as p, and it can't be 0, or else it would have finite order. And 3p can't be the same as the previous ones, or 4p or 5p. Turns out that if it's going to have infinite order, they all have to be different, all the multiples of p. So as soon as I have one point, it doesn't make sense to say really how many there are. It's just going to be infinite. But it turns out that you can look at sort of different how many infinite families, genuinely different infinite families there are. It's very analogous to measuring the dimension of a space. Like if I look at the whole plane, all this infinite plane, I can't count all the points in the plane. There's an infinite number of different possible points. But there are two different, genuinely different directions to go in. That's what makes it two-dimensional. And in a sense, if you look at all the rational points of infinite order, there's something called the rank of the elliptic curve. And then it measures sort of how many different families there are. So it's analogous to the dimension of something. Again, very hand-wavy, but I don't want to go any further on that. What we'd really love is a formula for the rank of an elliptic curve, and then we'd apply it to this guy. If we had something that just took this n, which is a number, we generate this elliptic curve, we go through put it through some crank, some big formula, and it just spits out the rank, we'd have a solution to the congruent number problem. If the rank was 0, then there would be no solution. There would be no points of infinite order and no triangles. It's not a congruent number. If the rank is bigger than 0, if it's 1 or more, then there would be infinite order points, and we say that n is congruent. We'd love this formula or procedure or algorithm to be effective. We'd like it to actually give us an answer in some finite amount of time. That's very much in contrast to the hopeless algorithm for triangles from way before. Remember, we could just list all the Pythagorean triples and try to find a scaled version of a triple that actually created this. Let me go back to that just to emphasize that connection. Remember, we had this strategy of taking triples, and here we found, oh, this had area 180. I'm not looking for area 180. I was looking for area equal to 5, but it was 36 times 5, and so we scaled it down, and we have the right area. But remember how hopeless that was. If we keep looking and looking and looking and we don't find one, we don't know. We might just have not looked far enough. Like this one was an illustration that we had to look incredibly far to get a measly 157 for an area, not a complicated number. So there is sort of a pseudo-algorithm for this, but it's never guaranteed to stop, and it's really not a good way to look. And it's definitely not a way to ever prove that a number is not congruent. So we'd love to have a formula for the rank of an elliptic curve, an effective formula that we really can calculate. Now, the rank of an elliptic curve happens to be extremely subtle, but that has good and bad things. It means that it's really hard to be sure you have a formula, but it does mean that there are very unexpected connections. So I'm going to start getting even more hand-wavy now, but I'm going to talk about an unexpected strategy for trying to get at this idea, trying to get the rank of an elliptic curve. And I'm not going to talk about it directly. I'm going to give you a vague description, and then I'm going to talk about an analogy. As always, I like to talk about toy versions of the real problem, because they still get at the idea. This is really infinite information. We're talking about all possible rational numbers, and we're looking at things of infinite order. We're specifically looking at things that don't kind of cycle back to 0 like a clock does. But an interesting thing is that it turns out that if we combine lots of finite information, but in an infinite way, and I'll give you the example in a minute of how that works, we can get some information about this. So what we do is we, instead of using ordinary numbers to satisfy this equation, x cubed, y squared is x cubed minus n squared x, we can try to use clock arithmetic. we can put in y's and x's that have these weird properties, like when I take 2 times 6, it's equal to 0. Okay, so we're going to actually look for solutions using clock arithmetic. It's called z mod p, and it turns out we only have to use prime numbers p. So we actually look at a clock with like 11 hours or 17 hours or 23 hours. And it turns out, because clocks only have a finite number of hours, this is a finite problem. You can count all the possible solutions using that kind of arithmetic. Now we do it for all possible primes p. Now there's an infinite number of primes, so that's what I mean by combining the finite information. We count solutions using clock arithmetic, but then we combine them into this massive combination that looks at all primes at once. Turns out you can combine that into something called an L function. And then we bring in infinite analysis in a very different way. We do calculus on this L function. And one of the things, this is the first time I've mentioned this word, I think, in this whole talk, but it actually turns out to be central to the idea of Burch and Swinnerton-Dyer. So far we've been doing a bit of geometry, a lot of algebra, and a lot of number theory, a lot of very finite, discrete kind of analysis. And calculus is all about the infinite and definitely using irrational numbers all the time. And it seems surprising that that would have any relevance to this, but it turns out for the last 200 years people have realized that there's a lot of number theory problems that you can translate into a calculus problem. Okay, so it turns out that the L function gives a lot of information about the curve, and I can finally tell you what the Burch and Swinnerton-Dyer conjecture is. We construct this L function, and I'm not going to actually even give you the definition, but I'll show you an analog in a little bit in the last part of the talk. We construct the L function. We evaluate it at the input 1. It's a function. You can put in any real number, in fact, any complex number into it. And turns out that if you take L of 1 and you look at that number, the conjecture is that when that's 0, that's exactly when the rank of the elliptic curve is bigger than 0. And that's when you have infinitely many rational points, and that would be exactly when you get a congruent number. So this applied to the congruent number problem is you take your number n that you want to test, you build this elliptic curve, you make this L function, and then you do some calculus on it. In this case, it's actually very simple calculus. It's really just evaluating it at 1, although it turns out you need calculus even to make sure that it makes sense, surprisingly enough. And you see whether it's 0. And if it's 0, the answer should be yes. Now this is just a conjecture, though. It's not prove that this is really true. It turns out, though, just in case we do actually ever prove that, it turns out that we'd probably be able to prove more, and this is the full version of the Burch and Swinnerton-Dyer conjecture, is that you do some more calculus on this L, and it should give exactly what the rank is. And I might say a little bit about that at the very end of the talk. Okay, and that's a good place to stop this section, though.